Okay, I think we are live.
Yeah, I think we're live. Let me just read the audio.
Hello. Are you visiting us today? Just today, tomorrow. Yeah, great. Let's bang the
So is that everything on set, Simon?
Yeah, it should be on. I just want to double check. The audio.
Is that okay, Simon?
Yeah, that was all.
Okay. So I can make this
Yeah, we can zoom in a little bit to the slides.
okay. I'll do it right now. Just do the slides.
Sorry?
There is current revenue and up here, there is your raw miners. Oh, raw miners. Yeah.
Sorry.
Okay.
Raw miners is basically here.
Okay.
We have geo.
What?
We can't go over schedules of program for that.
So the new following that is 21st.
If we have much of time, we can talk in the next day, so it's not like we can ask it to about stuff.
Who do we have the next day? No, Tom is definitely going to get it.
Yeah. He's already.
Yeah.
We can give it up.
So, I mean, it's going to be hopefully. If you drop
It drops it all because we
We have the doctors visiting us on the day of this geo. 21st.
Yeah, that's an interesting.
Do you know what is counting condition?
Yeah, I think so. Let me check on the spreadsheet.
I mean, I suspect that Rob most likely would also be visiting Stanford as well. So we could talk to him and find out, like, for example, we could
Give me stuff.
go, well, go visit Stanford on Tuesday. I don't know.
Which day is the program?
21st.
21st, yeah, we have Raw, but I don't have the dates there, so but maybe Lager.
Oh,
Lager is, everyone there will be on.
I mean, it's different things. We could simply ask Rob to give a talk.
Yeah.
Yeah, I mean, on 21st, he's going to be there, so.
That's gonna be here.
Yes, here, yes.
So, yeah.
So,
Well, I think either that, or we try to apartment. Some other site. I can't imagine, I mean, apartment would be local. What's the schedule looking like? Okay, we should probably get started. Sorry, we've got our.
Thank you, George.
Okay, we are very happy to have Victor Evo going to tell us about one of the aspects of disintraction wormholes.
Alright, thank you so much for having me. So I'm going to talk about a paper that I work on with Hyphen. He's a third year student from Stanford. And it came out a few weeks ago. Where we basically studied the most determinant around these axion wormhole solutions in the system. We kind of started wanting to know about the phase and things like that. So we learned a bunch of interesting things about the determinant. In particular, the relation of these wormholes and operator insertion picture and what you can learn from this calculation. So anyway, without further ado, one motivation is maybe to understand the gravitational path integral a little better. I'm sure everyone knows what the gravitational path integral is, but we can remind ourselves that it's very useful. It gives structural corrections to near external black points, entropy, phase curve, main resistance holography, and the list keeps growing. We learned in recent years that sometimes we need wormholes. For example, wormholes are necessary for the unitarity of black hole evaporation. Bracket wormholes are necessary to solve some subactivity puzzles. As shown, this can provide e-mean, little or matrix 1. And wormholes in our universe are interesting because they could give correction to cosmological observables. So you could, for example, in a density matrix, have some wormhole connecting the Brownian cat. That's some connected contribution. And you have a wave function of two universes. It could also have some wormhole connected contribution. And of course, it will include off-shell wormholes, but it's always nice to have a saddle. And today we're going to be talking about a specific saddle called the cedar axion wormholes. They were found by Rob Myers in '88 and rediscovered, I think, in 2023 by this group. They are basically very nice FRW solutions with starting equalizers, so it's like a tau directionized d-1. So they are SOD symmetric, and the scale factor A of tau is periodic in Euclidean time. So basically, you get a compact Euclidean solution, you identify the tau direction, you end up with some Euclidean manifold like this. You can also extend these things to Lorentz signature. If you do from the minimum of the scale factor, when extrinsic curvature is 0, you get a big branch cosmology. And if you continue from the maximum, you get expanding universe. Today will be interesting in understanding the Euclidean solutions better. We'll see that we get lessons that hold for basically all.
So, can you say more about these solutions? This looks like an ordinary considered solution, but then.
Yeah, the point is that the expanding universe is very close to the cedar, kind of, because if you continue from here, the effect of the flux that we're going to discuss later is very small. I'm going to tell you more about the classical solution.
The thing on the left is that.
That is
S1 plus S2 or S1?
That is the tau direction, and for each given tau, we have a sphere.
But a circle is a sphere, right?
Each circle is a sphere, and we identify all tau. So this point is the same as this one. Yeah. We're going to be talking in more detail about the classical solution later.
This one is taxes, that's the difference.
Yeah. Topology. Yeah. But anyway, I'm going to be telling you the full solution of it. But before, let's talk about the theory that we're studying. We're studying gravity, kappa squared G Newton, coupled to a d-2 form. The d-2 form field is B, and FdB is the field strength. F respects flux quantization, of course. And since we canonically normalize its action, flux quantization condition usually a coupling. Similar as in Maxwell theory would. If you don't have a 1 over E squared here, you're going to have it somewhere. So anyway, flux is quantized, so the integral over this form on d-1 dimensional surfaces is quantized like that. It's going to be important for us. And this F here is some coupling constant, sometimes we're going to refer to it as magnetic coupling constant, and it's related to the axion decay constant of the dual theory. We're going to be considering some convenient choice of units where the cosmological constant, which, sorry, I forgot to say is positive, has the antecedent equals to 1. We can basically pick these convenient units by starting from the original theory and rescaling all the coordinates, such that we get antecedent equals to 1. But then all the factors of kappa squared and F squared that are right later should be understood as being the physical ones, with these factors of antecedent are sorted. Before we talk about the wormhole, I'll give you the sphere solution for contrast. So there is, of course, in this theory a background where the d-2 form background is trivial, and we just have a pure gravity solution that is the sphere. So you can write this FRW form like this. So you have a bunch of different tau points, and each one of them you have a sphere, like we were discussing earlier. The scale factor here is sine of tau, so we manage the 2 points, which are the ancient pole of the sphere. And then we can consider what happens if we allow now some background flux field, which is the F to be turned on. And if we do that, instead of having the sphere, we have now some more general FRW with alpha of tau not equal to sine. And the d-1 form background that we turn on is basically a volume form along the ST-1 slices. It's completely asymmetric there. And it has this flux parameter Q, which is quantized because of the flux quantization condition. So, okay, we can just take this thing and now look at the modified Friedmann equations. And they look like this. So they're very similar to the de Sitter ones, but they have this extra term here induced by the flux. So let's think about what happens if the charge is very small, more specifically this combination of the Newton and the charge is very small. So there, you basically have a sphere solution almost everywhere, because this term is negligible. But then as you approach the pole and the antipode, A becomes very, very small. And at some point it will be small enough that this term starts to dominate, and will eventually cancel against this one. So instead of A approaching 0, you approach a minimum now where A prime is 0. So basically that's what I was drawing here. So you basically have a maximum of A, right? It's about the same as we had in the sphere before, it's about A equals 1. Then we start decreasing, we get to a minimum, it bounces right back, it starts increasing again, and decreasing, and etc. And you have some oscillatory pattern with some period. So the point is that if you just took the solution as it is, you're going to have some infinite thing. That's not very interesting, but we can get a compact manifold by identifying the solution along the tau direction. So we can identify after one period, in which case we get this, like we discussed before, or we can do after 3 and then get this solution. And another interesting aspect of the solution at very small charge is that here the metric is almost of a sphere, right? But near the handle, then the metric has another simplified form, which is the form of a flat space wormhole. Because the idea is that if we zoom in on the handle, the cosmological constant is basically negligible, and the Friedman equation is dominated by the curvature term and the fluxes. So basically you have the same equation of motion as a wormhole in flat space. So the metrics of this form here, you have a nice form for 0 dx, and you have this scale here in front, which is basically the size of the handle or size of the wormhole or not, which is fixed by this equation.
Sorry, can you repeat again why you get a negligible cosmological constant?
Because the cosmological constant is the A squared term. And when A is very small, it's much smaller than these two.
Yeah, I guess my question is why so small?
Well, it's not that it's small, but instead of at small values of A, it loses against the other terms. Because the other terms decreases with A, right?
Yeah, I was asking what you're saying basically that this handle has a very small length, right?
Yeah.
Yeah, that's what I understand why.
Oh yeah, because the minimum value of A is fixed by the charge, right?
Yeah.
So if the charge was 0, it would be 0.
Oh, I small charge.
Yeah.
Okay.
Yeah, so
yes.
that was small charge.
Okay,
Sorry. Yeah, sometimes I'm talking about small charge a lot because they're kind of the most interesting solutions, but yeah, thanks for clarifying this one.
Yeah, sorry, I missed that.
Yeah, so at small charge, we have this very cool physical picture where we have basically ends for the n oscillation wormhole, we have n spheres connected both by antipode via flat space wormholes. And another interesting point is that if you have small wormholes, we know that they should be related to operator insertions. So these are ideas that was first, I guess, kind of developed by Coleman and Strominger when they were thinking of small wormhole mounts being operator insertions. But it was then refined by Extremal and Susskind, where I think they say in this following form, that is maybe a bit well defined, a bit better defined, that if you have a wormhole connecting two big ambient spacetimes, we can replace the effect of the wormhole at large distances by a sum of bilocal operator insertions with bilocal meaning you have a product of two operators in each ambient spacetime. So the motivation is that you can basically have a bunch of states propagated to this wormhole, and from the perspective of each spacetime, the effect of this state is basically mimicked by this operator insertion. In principle, to get the full effects of the wormhole, we should sum over infinitely many operator insertions. They are constrained by things like symmetries of the problem. In our case, for example, they have to be consistent with the amount of flux going through the wormhole, that little number below n. But anyways, that's the principle. And the Cij here are EFT coefficients, which basically are the coefficient here in front of each bilocal operator. They are unknown, and you need to find them by matching the calculations in the wormhole side and in the operator side. But the useful thing is that once you have these EFT coefficients, you have them forever. So you can use them for any calculation where you can displace in a small wormhole by operator insertions, even if they're in the Sitter ADS or whatever.
Sorry, you say again, like what determines how can I compute this Cij?
You compute things on the gravity side and in the operator side.
And then just do some matching.
Yeah,
Gravity side and operator side goes need to have one example.
yeah. But once you compute for one example, you have for many, right? But that's the principle of FT in general, right?
Yeah,
FT has general coefficients that we need to fix by one computation, but then once you have them, you have them forever. So let me tell you just two more things. So we have an integral over x and y here, right? That's because on the wormhole side, we should integrate over the wormhole mounts, which are basically some moduli. And this means that in the operator insertion side, we should integrate over the position of the two insertions in the main spacetimes. And another feature here is that we sum over infinitely many insertions, but the sum really truncates quickly. Because operators of higher dimension are suppressed by powers of the wormhole scale. So the point is that the sum really is dominated by a few low dimension operators. In the coolest version of the approximation, they are approximated by one leading operator, and that's precisely the approximation we're going to discuss for all wormhole. So for these axiom wormhole that we're discussing, the leading operators are these magnetic operators or Toff operators k plus minus n that create or destroy any units of magnetic flux. To be more specific, they modify really the Bianchi identity of the theory by adding some defects somewhere. This was discussed in some level by Coleman and Lee, and better said by Wheaton this year. So basically, you have a picture where you have this wormhole with some flux flowing through it, which can be replaced by a picture where you have two spacetimes. You have some flux here, which is absorbed by this operator, and then spin out on the other end by the other operator of opposite charge.
But should we interpret, I guess I'm a bit confused about the philosophy here, because indeed we have small wormholes.
Yeah.
But we have like an entire set of saddles that go from small wormholes to big wormholes. So somehow for the big wormholes, we cannot do this.
For the big wormholes, you cannot. Yeah, thanks for saying that. This is also the small wormhole.
But then, since it's a continuous set of saddles, that's fueled by the flux.
Yeah.
Right?
Yeah.
Isn't it a bit weird that we can only?
Yeah, I guess I'm saying that for a given wormhole, we can do this picture, not for the full sum. I wouldn't be claiming that the full sum over charges is well approximated by this operator insertion picture. It's more that you can imagine one saddle with some value of the flux, and if that flux is small, we can do this idea. Yeah, but I agree with you that it doesn't make so much sense for the finite cube case. You had a question too?
Yeah, like it's related, and also I should not ask you this, but it's because it's also related to what me and Haifeng are doing, and we should understand it better. But here, I mean, we have a closed universe, right? So like we don't have a symptotic boundary where we say, okay, the charge is some boundary charge matter.
Yeah.
Like it's a parameter.
Yeah, it's a parameter of the solution.
Then
You're trying to understand.
if in this case, like you still have a family of saddle in which you just tune the parameter, all of them are like are valid saddles. Isn't that kind of weird? Like if you have a boundary charge, okay, I just fix this charge to this number.
Yeah, we're not saying what's the philosophy here, like how we should sum over these wormholes or anything like that. I'm not saying that we're using boundary.
It's just like in GPI, how do you isolate a specific?
The Cartesian path integral has many saddles, and that's one of them, I guess. That like you allow to have saddles with different fluxes and etc.
Yeah,
but they all exist in the path integral, and one should study their contribution, I guess. That's the philosophy here. We're not saying that we're doing some calculation where we isolate the charge and etc. I'm saying that there will be solutions with many charges and many different parameters, and we're studying one of them.
Maybe, just are you gonna come back to the large wormholes? Or
We are.
Okay.
We're just going to doing this small tangent because it'll be useful later. Sorry for the tangent. But you can an interesting tangent. I think the small wormhole and operator research is very interesting. Which basically we're studying these guys that I want to understand the relation. But anyway, so we have that. And final discussion about small wormholes. So the idea is that this wormhole has small charge. You can think of being a sphere with two operator insertions. And we can do some sort of EFT matching by noticing that the coefficient Cn minus n of the insertions have to basically go as the action of the wormhole. So the three-level part is kind of obvious. But there could be principal some contributions for the one determinant. Also, in principle, we should integrate over x and y like I told you before, right? But it's not clear what is the range of the xy integral at the level of this picture. Because from what I was telling you, it's like integrate over x and y everywhere, right? But if you just look at the saddle, the two mountains are very specific spots, right? They are the pole and the antipole. So would it even make sense to integrate over x and y in general? Later, we're going to see the calculation actually forces us to integrate over x and y as follows. You can integrate over x and y together in the sphere as much as you want, but the separation of them is going to be only allowed to fluctuate a little bit, because the antipodal configuration is an extremum of the two-point function of these operators in the sphere. But anyway, that was all for small wormholes for now. Let me tell you about the biggest wormholes, since we're big wormholes. So you can basically increase the charge as much as you want, and at some point you're going to land on a critical charge Q, which is the maximum charge that these wormholes can have and still be real. So this value of QC is written like this. If I pick the Sitter units, you depend on G Newton and L the Sitter. And these solutions have a fixed value of A equal to some AC fixed by that. So they basically are literally just cylinders. In Lorentz signature, they become Einstein-style universes, so we're going to call them sometimes Einstein wormhole. These solutions have zero action, so their length is an unfixed moduli. So before we were discussing all these oscillating wormholes, right? And their length was really n times a fundamental number, which is the number of the smallest period wormhole. But these guys' length can be whatever, because it's a free moduli. So that's the difference between the extremal and the non-extremal wormhole.
This is analogous.
Oh, sorry,
This is analogous to like Spectral de Sitter versus Mariani, it's like space-time versus spatial wormholes.
Yeah. I think so.
Just to make sure the action is independent of this L.
Yeah, the action is zero. So
Okay.
it's independent of L. Because if it's zero for L1, it's zero for L2. So if the community of the length of this wormhole is given by a parameter n as follows, so it's this 3 factor times n. The idea is that if you take the non-extremal wormhole and we continue the charge to the extremal value, we're going to land on a specific extremal wormhole with a given value of length. It would be like n times something. So if you had the n cycle wormhole, you're going to, as you continue Q to TC, you got an extremal wormhole with that size, with n an integer. So it's convenient to think of the extremal wormhole as having a length parameterized by n. N can be whatever, but when it's an integer, we can think of it as a continuation of a non-extremal one. But anyway, so that was it for the classical action. Any other question about the classical action, or we can?
So the classical, oh, sorry.
Yeah.
I had a question about the classical action.
Yeah.
If I have n of these copies in the limit in which the wormholes are small, you obtain n times.
This sphere action, yeah. So they have a whole paradox associated with it, which is that if you sum over all of these wormholes, you get a divergent answer, right? Because the wormhole with n cycles has more negative action to the wormhole with one cycle. So in principle, we have a whole sum, which if you sum naively, will be dominated by the guy with n equals infinity. So,
Is it true that the answer is well approximated by an exponential of e to the
no, because you don't have the 1 over n factorial that you have on the sphere. Because the sphere have full permutation symmetry, right? But these guys are just have cyclic permutation symmetry. So you have a 1 over n instead of 1 over n factorial. So that's why there's a puzzle still. I'm going to comment more on the future directions part. Anyway, now let's talk about the one determinant. So to show the one determinant, should expand the metric and the form fields are on the background. And we're going to expand them like this, so that's the GBV. And the D-2 form fields, you can really think of them as two forms after you with epsilon contrasted. So we're going to be referring to them as metric and two form variables from now on. And you define a measure from them by defining first a local norm. Think of the fluctuation as some collective field phi, with some vector with metric and two form variables. You define some norm for these fluctuations, and this local norm fixes a unique local measure that you can then use to do the path integral. Here are some general two-parameter family of local norms you can write down for these fluctuations. We're going to be fixed on P1 equals to P2 equals 1 here, but in the paper we explore more. We also have to gauge fix the theory somehow, because we have both diffeomorphism and the gauge invariance of the D-2 form fields, right? So we do this by picking some gauge conditions here, and adding some gauge fixing terms, and some proper gauge fixing goals. here the gauge fixing condition, this is the donor-like one, and this transverse gauge condition for the forms. And we wrote here some two-parameter family of gauge fixing parameters. We played with them in the paper, but here we're going to be using alpha equals 1 and beta equals half, which is the usual denominator gauge fixing, and harmonic, I think transverse gauge fixing is the name for the forms. Anyways, that's some more details. But the point is that after you do all of that, the path integral becomes some C Gauss contribution and some Gaussian integral over the fluctuations of the metric and the true form. Since this is some Gaussian integral, you can express them as a function determinant up to some 0-1 contributions, which is a bit more thinking, because you have some 0 eigenvalues around this wormhole that we're going to be discussing later. So you can discuss this functional determinant by solving the eigenvalue equation for n. The eigenvalue equation for n is this ugly thing that I wrote here. Since the background is not maximally symmetric, we cannot solve it exactly, so we need numerics. Numerics becomes slightly easier after you use SOP invariance of the background to write both the metric and the true forms in terms of a bunch of different SOP representations. And the SOP invariance implies that these guys all decouple from each other. So here we can basically think of these fluctuations as effectively 5 scalars, 4 transverse vectors, 1 transverse true form, and 1 transverse tensor, transverse traceless tensor. At the end of the day, you expand all of these fields even further to harmonics. Let's say the scalars expand to spectral harmonics. And once you've done that, you basically get the eigenvalue equation becomes some differential equation of the tau direction, which you can solve by discretizing the tau direction along some gradient. But anyway, after you do all this boring work, you finally find the spectrum. Here I'm showing the spectrum from for d equals 5, some intermediate value of the charge, q equals the maximum value at 0.7, and n equals 1. So I show you here both the scalar sector eigenvalues. There are the 5 sectors that we discussed before, with angular momentum L equals 0. Here you have both red and blue modes. The red are positive modes and the blue are negative modes. You can see here that you have a tower of negative modes because we're dealing with Euclidean gravity, right? So the conformal factor problem implies there is infinitely many negative modes, and we will discuss how to deal with them in a bit. And for a different example, I also showed here the tangent transverse vector sector. That one only has positive modes. Indeed, we find that only negative modes of the background are in the scalar sector. But to be more precise, I should tell you that the tangent transverse sector has 1 0 mode. Maybe you can see it right here, it's the green dot, which actually has a very nice physical interpretation. It has to do with some twist moduli of swap. But anyway, before we proceed, let's discuss negative modes. So since we're dealing with Euclidean gravity, there are infinitely many negative modes. We need some way to deal with them. We're going to do so by treating each negative mode as the following Gaussian integral. Integral dx into the x squared, right? So that integral in a vacuum doesn't make any sense. You could try to analytically continue to regularize it, but it's still ambiguous. But you could imagine basically defining this Gaussian integral for first a negative coefficient from x squared, and then another continuing to this coefficient to be real and positive. There is some ambiguity here. You're going to get a difference if this is a 1 minus I epsilon or 1 plus I epsilon. And you need to basically pick a prescription. Here we're going to imagine that we have 1 minus I epsilon in front, in which way it's regularized wrong sign Gaussian gives you minus I times the contribution of a right sign Gaussian. Another way that you can think about it is that after you put this 1 epsilon, you can rotate the original x contour to the imaginary contour while in the direction of maximum increase. Once you have this 1 minus I epsilon. We can implement this prescription in mode determinant calculations by imagining that the theory has a slightly imaginary Planck's constant. So 1 over h bar really has a 1 minus I epsilon in front of it. So if we do that, each wrong-sign Gaussian is going to come with a 1 minus I epsilon in front of it. It's going to be regularized exactly like we discussed. So if you have e negative modes, the overall phase would be minus I to the ne. The issue, of course, was much deeper here because ne is infinite. This was the Euclidean gravity. So we need to regularize this even more. And one can do this by understanding E divergence as basically the number of points in space-time, or equivalently, the number of eigenvalues of the Laplacian. The idea is that at very short distances, there is a mode, which is this overall scale factor of the metric, that decouples from all the other modes, and whose eigenvalues are approximated by eigenvalues of the Laplacian. So for every eigenvalue of the Laplacian, you get a negative mode. We call this overall number of eigenvalues of the Laplacian NSB. So basically, the subtraction of the number of negative modes by this has a better chance of being better defined, and we call this thing n minus. So the idea is that we can think of the phase as being minus r to the n minus times this divergence here, and we can then think of this divergence, and that is the biggest jump here, as a local divergence. So the idea is because this is minus I, one factor of minus I for every point in space-time, that is a local divergence, and then you can deal with this by solving to proper calculus of material. So assuming you do this, the phase ends up being finite, this regularization, and equals to minus I to this difference n minus. In practice, computing n minus is actually quite easy. So you just study your eigenvalue problem with some regularization where you have a finite number of modes. If you do that, there's a finite number of negative modes and a finite number of eigenmodes of the Laplacian. Scalar Laplacian, to be more specific. Here we basically find that n minus comes only from the scalar sector. More specifically, since we're decompose the modes into harmonics, n minus is really a sum over different harmonic representations. And at each of them, the number of modes that you have are basically only have to do with the number of grid points you use for the tau direction. But anyway, jump these details aside. You, using this philosophy, you get an overall phase from the wormhole, which is I to the 2n, or minus 1 to the n, when the charge is non-critical, and I to the 1 plus 2, the integer value of n for the extremal wormhole, and we n define as we discussed before. But anyway, so here, the interesting part is that the non-extremal wormhole has an oscillating sum over them, right, because of this minus 1 to the n. And we're going to understand this extremal wormhole phase better later. But let me tell you other features of the spectrum. So the good thing about the spectrum at small charge, at the very least, is that the eigenvalues that you get are basically the ones, let's say for n equals 1, of the sphere in pure gravity, with maybe this d minus 2 forms decoupled. Except that you get a few extra modes. So the eigenvalue is basically what you got in the sphere, with finally many new modes, and they are basically divided as follows. You have some like modes at the L equals 1 scalar representation. If you have inside the wormhole, you have 2n of them, but each comes with a degeneracy d, so you have 2n times d of them. Half of them are positive, the other half are negative. You have some new zero modes at the L equals 1 transverse vector representation. You have one set of them, but they come at the degeneracy of the L equals 1 harmonic is d minus 1 over 2. And that actually should tell you something, right? This is the number of generators of SOD. And indeed, you can interpret these modes as having to do with twisted wormholes, where instead of gluing them after, with basically identifying the coordinates, you can glue them after identifying the coordinates of 2i isometry. And you should integrate over these different wormholes, and basically the zero mode that you found here is telling you that if you didn't do it before.
But that's a compact zero mode.
That is a compact zero mode, absolutely. You can relate the path integral over it to the path integral over SOD. And you can figure out the prefactor, which is going to take. And you also have some new harmonic forms, specifically t equals 3, because the solution at t equals 3 has harmonic 2 forms, right? Because that's 1 times S2. But that's kind of a boring compact zero mode that always ends against some term in the ghost determinant, so we don't discuss it too much. It's kind of boring.
Sorry, I didn't understand the last zero mode. Could you describe it
Oh,
again?
So basically, the last zero mode has to do with the fact that if you're studying a form theory, the zeros of the form theory decoupled from gravity are fixed by basically the Betti numbers of the background, right? So since we're studying a 2 form, if you have harmonic 2 forms in the background, we have zero modes. And these guys in particular are incapable from gravity, so you can understand the theory from the form perspective. So because you have S1 times S2, you basically have some harmonic 2 forms associated with the S2 direction. Equivalently, you can think of them as harmonic 1 forms related to the S1 circle. Yeah.
In the language in which I dualize the 2 form, is this 0 mode corresponding to the shift symmetry of the scale?
No, it's different.
It's a different.
Yeah, it's more that there's a conspiracy on electromagnetic duality that the two sides match, but you cannot match this specific thing to a thing in the scalar side.
Okay.
Yeah. Actually, there's a very nice paper by Aaron where you can show very specific how the duality works and how orders match each other, but it's a bit not trivial how it happens. I'll be happy to explain in more detail later. So yeah. But let's talk about the wormhole position modes because they're quite cool. So these light modes that I told you about, right, and the scalar representation, you can basically plot their norm along the radial direction, and you can find that they're basically localized to the wormhole throat. So basically, their density is localized to the throat as the Q goes to 0. And you can find here that they're light modes because their eigenvalues linear in Q. So they become more and more zero modes as they Q to 0. Another interesting thing is that the negative modes these negative light modes are gauge fixing invariant small q. So you can play around with the gauge fixing parameter, change it, and this guy basically stays the same. But the positive one is strongly gauge fixing dependent. But it actually becomes quite clear after you think of the following picture. So we can basically think of these wormholes in flat space first. So if you just had these wormholes in flat space, right, they end up in two big infinity Fourier asymptotic spacetimes, and there are some zero modes associated with moving the wormhole out in the asymptotic ambient spacetimes. There are d plus d, or 2 times d of them, because there are 2 times d main displacements like this. However, in our problem, we have the 2 wormhole mounts ending up in the same big sphere. But since the sphere is finite, now they can interact through the bulk. So these previous zero modes are now lifted. To be more specific, there is a motion that corresponds to displacing x and y together along the sphere, right? So that's basically a coordinate transformation. You can do this along some isometric sphere or something like that. And you would think that this would still be a zero mode in the gravity side of the calculation. But we added a gauge fixing term. So this zero mode's got an action because of the gauge fixing term that we added. The action is positive because the gauge fixing term is positive, and it's strongly gauge fixing dependent, as indeed we saw in the last slide. But there are also alternate modes, right? Negative modes, and they have to do with moving x and y together. And moving x and y together is a physical displacement because you change the gauge invariant quantity, which is the distance between the 2 wormhole mounts. So basically, we learned that bringing them together is a negative mode. And we can think about this a bit better from the effective operator side, right? Just remind me talking about small wormholes still. So from the effective operator side, we can think of the whole wormhole as a sphere with 2 bilocals. So the path integral should be the path integral in the sphere times the effect of the bilocal, which is the EFT coefficient, and the integral over the xy position of the 2 insertions. But as we learned before, we should integrate over x and y while keeping x and y almost antipodal from each other. What's the justification for this? The justification is that we can take this 2-point function and we can basically evaluate it explicitly in a sphere. To be more specific, the easy way of doing this is use electromagnetic duality to relate these guys to e to the I axion, and then basically solve this path explicitly. And what we learned is that this 2-point function has an extremal when x and y are antipodal from each other. This makes sense because this is a 2-point function in the sphere. It's the Sitter invariant, so it should only depend on the distance. Antipodal configuration is the furthest away the points can be. Therefore, it must be either a minimum or a maximum of the 2-point function. And by further inspection, you can fix x to the antipode and then move y away from the antipode. And what you learn is that this is going to increase the 2-point function. So this means that the saddle is an unstable saddle. Here imagine that it displays x2 by delta tau 2 from the pole. But since this is a radial displacement from the other pole, this is really made of d-independent displacements, right? So there are d-negative modes associated with this position moduli, exactly as defined in gravity. In summary, I think the coolest thing here is that this wormhole saddle has a clear interpretation in the effective operator picture, which is that you have the two operators and an unstable saddle, and you integrate over small fluctuations around. Indeed, we get the correct phase by doing this, right? So the path integral here is the one in the sphere times the operator insertion contribution. The sphere gives us OGC phase, which is I equals 2, and this path integral over unstable displacement gives us minus after d. So you get I squared, precisely as we had before. And for the wormhole n cycles, you have basically n spheres, each of them with the same type of operator insertion. So you get the same phase to the power of n. Is this wormhole unstable? Maybe a relevant question, if it contributes to the path integral or not. To do this, you really should study the appropriate steep descent contour, define some original contours for the path integral like it cross, and see if these wormholes cross appropriately. We haven't known technique to do this, but it's an interesting future direction. But let me give you an example of a similar unstable looking solution that does do something, and we like it. So you could consider a sphere with basically a wood line particle in it, and you consider the saddle where the wood line is in a great circle. So this is an unstable saddle because I can basically split the wood line to the pole to the antipole. Now we decrease the action. This has d-1 negative modes. Nevertheless, Edward and etc. Has argued that this is basically associated with the maximum entropy state for our observer in the sitter. So we think this contributes sometimes. And it has some nice physical interpretation. In particular, it can show that this is a subleading correction to the scale path integral.
So can you comment on what Van Reed and company did to show that it's stable?
Oh yeah, so there's different ways of defining stability. I think this phase is kind of different, similar, and orthogonal to it. But the claim that what they do is the following. They study the fluctuations, they impose constraints first, like Hamiltonian momentum constraint, which makes sense in Lorentz, but they kind of extend this to Euclidean as well somehow. And then they study the gauge invariant perturbations of the subsector, and they look if this thing has negative modes or not. So it's like some canonical gravity-inspired notion of stability. So that's what they did. There are also some rule of thumb by Tomaro that he did. Instead of doing the positive measure for the path integral like I defined, it allows you to have some negative directions associated with the scale factor of the metric. And if you do this, you can also get some other notion of stability. So they're like basically the set of fluctuations after we rotated things first. So anyways, but what they did is this canonical gravity thing that I mentioned.
And that's different than doing a gauge fixing.
Yeah, that's different from the phase. Yeah. From another things that it seems that this thing of rotating first and then having a gauge fixing term is not gauge fixing invariant, the phase or stability that you get in the end. But our case, even though it's a bit weird and you get a phase in the end, it is gauge fixing invariant. Even if you are a negative gauge fixing term to the upper, which is kind of wild. I can comment more on that later.
So can I ask a question?
Yeah.
I must have missed something, but so here you're talking about stability of one saddle, right? Like you take one wormhole, you do perturbation around the saddle, and you look whether you have negative modes and whether you have a runaway agent with that negative. So like the control factor problem.
Yeah.
How did you get rid of the infinite family of wormholes?
Infinite, we're studying one saddle.
Well, you're studying one saddle.
One saddle.
Like, are you worried that there are all these other saddles?
We're not doing the full resummation. We're studying the one with the term there are one saddle and see what it teaches.
Yeah, but isn't this telling you that even if your saddle is stable, perturbatively might be non-perturbatively unstable?
Perturbative? Well, you could have other more leading saddles, I guess.
Yeah,
is that what you're saying? Yeah.
And if you have an infinite family with negatively divergent action, that is
I'm not that. Yeah, but I'm not claiming that this saddle is stable or not. I'm just computing the phase. But yeah, even if you show that it's stable like they did, you can still have the complaint that you're saying.
Then like it's stable perturbability, but not.
Yeah, but you need to get rid of the other setup somehow. I agree with you.
Okay.
So and for that, you need the sequence and contour. I think that's the
Right.
short way. But anyways, since we have a very few time, I'll kind of go very quickly over the rest of the stuff. A quick call at the Einstein wormhole, you can understand the phase that we got as follows. You can look at the physical degrees of freedom of the Einstein wormhole in Lorentz signature. This consists of instability, that's a well-known stability of the Einstein-static universe. If you continue to put in a signature, that's the path integral over it is kind of like the path integral of a tachyon. It actually has a minus sign in front of it, so it's like a tachyon with negative sign kinetic term of positive mass. But anyway, the point is that you can basically say this path integral in space, and it exactly matches what we got before. So you can understand the phase that we got from the extremal wormhole as coming basically just from the instability of the Einstein-static universe. I think it's quite. But that was a quick comment. Another comment is that here it is exactly this. The phase of the path integral is exactly different instabilities. In the previous examples, the phase of the path integral is related to instabilities, but there's an offset. I'm talking here about basically the cycles in pure gravity that I studied with Zemo and 1. So the path integral of these product manifolds, which are the zeta times some internal thing, is some contribution from instabilities seen by someone in the static patch. But you also have the Pochinsky phase associated with the zeta that you live in. So there's an offset, and here we find an offset, which is interesting. One can wonder if this has to do with the lack of horizon in the wormhole geometry. There are some ideas that maybe this Pochinsky phase related to edge modes, and it would be interesting to understand this better. A quick comment, I'll not go over the calculation, but I'll tell you the gist. So we have the following relation: path integral of the wormhole over sphere answer should be the same as integral over operator insertions. We check that this idea works in the level of the phase, but you could also see if there's a match at the level of the dependence on Newton, F, L, the zeta, and things like that, some parametric dependence on both sides. But you can say, oh, but the EFT coefficient is unknown. So how is this even a check in the first place? The idea is the following. So the EFT coefficient, the relation between operator insertions and the small wormhole should be local. So the EFT coefficients that you get should not depend on the large scales of the big ambient spacetimes that they are ending up on. Otherwise, the effective description will be useless. So a physical principle is that the EFT coefficient Cn minus n should not depend on L and zeta. And that's why you can check more explicitly. There's basically an important principle that you need to assume to do that. So to take a ratio of two path integrals, in principle you should do heat kernel carefully, get rid of the divergence as well, and then you get some final part in the end. That's quite hard, and so that's not what we intended to do. But we have a contribution for a bunch of light, zero modes, and things like that. So we could wonder from there we could extrapolate what this ratio should be with minimal assumptions. So to do that, we basically have to discuss the ratio of the path integral in some space-time with a wormhole and the ratio of the path integral over space-time without a wormhole. I had something prepared for that, but since we have 1 hour, I think I'll just skip to the end maybe.
Well, I will second time.
We started late.
You still have like 15 minutes.
Yeah, but that's the last thing. Yeah, sorry about that. So let's look in more carefully. So take a joint operator G in a space-time n. We can define a path integral from that as follows. Take some field psi, some auxiliary field, and the path integral of psi with axion phi g5, that defines a path integral. So we can imagine doing this path integral, and here we can keep all the coordinates dimensional. So if G, we're going to assume has a dimension -2, we assume that G is like minus Laplacian or something like that. So if we do what we did before, where we define a dimensionless norm and then a measure for the field psi, we should first define a norm as being an integral psi like this, so it's a local norm. But since this thing has length dimension -2, as you can check by the fact that they are dimensionless, you need an overall scale here, mu squared. There's an arbitrary scale that enters the measure. And the point is that from this, you're going to get a measure for these fields, which are just going to contain a factor of the arbitrary scale mu for each mode running the path integral. The contribution of each mode contains a mu, but the path integral at the end of the day should not depend on mu. at least if D is odd. If D is even, it's a bit more subtle, and mu is kind of like a regulator. So from now on, we're going to be focusing on odd D. We would like to consider the ratio of the path D integral, as defined in the previous slide, in a manifold N and a manifold N naught, where N is N naught, but it has a small handle, and maybe a slightly deformed geometry. We're going to have two core assumptions. The first one is that the integral over individual eigenmodes in N naught carry over with minor modification to N. What does that mean? That means if I had an eigenvalue in N naught, it carries over to N with some minor shift. We check this is the case. As I told you, the wormhole, where we have a small handle, has the same eigenvalues as the sphere, like that. Sphere eigenvalues are still there. The only difference is that you have some new ones. And the second assumption is that the path integral N has a finite number of new line modes. Again, also the case for the wormhole, we have the line modes and the twist ones that we discussed. So we should be able to think of the path integral in the spacetime with the wormhole as follows. All these contributions that exist in the sphere before, part of them should resum to be the same as the usual sphere answer, or the N naught answer. I'm not saying there's a clear way of doing this, but some way of organizing the calculation should be able to do that. However, the new line modes do not enter here, so we need to include them by N as a contribution. And there could be some extra contribution, we call it Z handle prime, which comes from the overall correction to all modes, new UV handle modes, or anything else. Now we have a clear issue. Since the path integrals are mu independent in all dimensions, this guy doesn't depend on mu, and this doesn't depend on mu. Therefore, for this to be consistent, it must be that this product, Z handle low and Z handle prime, are mu independent on their own. However, since there's a finite number of modes running in Z handle low, this has an overall mu dependence, which is mu times the number of new modes, delta N low. Therefore, you must give a consistency that Z handle prime scales as mu to the minus delta N low. So you cannot just take the contribution of the new modes in some generic measure and be done with it. You also need to consider this correction carefully. The issue then is that the contribution for each term in the path integral is dimensionless, and mu has a dimension of energy. So Z handle prime cannot enter by have mu entering by itself. It must come with some mu actual scale, with some physical scale from the problem. In our problem, because we can deal with remove G Newton and F in some simple way, has only really two scales, which are the scale of the sitter and the scale of the wormhole. We propose that the only scale that enters Z handle prime is the scale of the wormhole. Basically, this Z handle prime should come with a contribution for a bunch of terms which are local or only sensitive to the new handle that we have in space-time. The physical intuition from this is that you can think of a picture where the path integral over the space-time with the wormhole splits into two. One is the path integral over the original space-time, and the second one is the path integral over this new handle, where basically treated as some instant on top of the previous space-time. So if that was the case, the path integral over these new handles would be something local as well. And it will be composed of two parts, right? It will be composed of some few light modes associated with moduli from the handle. These are the twist modes and the position modes. But it also comes with a bunch of non-zero eigenvalues that exist at the handle scale. So a bunch of eigenvalues that scale as are not the -2. So the point is that if you consider a product of a bunch of these eigenvalues, but you remember that a few modes are missing, since we consider the contribution separately in Z handle low, you're going to be having missing factors here. And you're basically going to have an overall mu dependence coming from that. This is similar to the path integral of the Schwarzian, right? We integrate over the Schwarzian modes, but n equals 0, 1, and -1 are missing, so we got a beta to -3.5 in the end. It's the same idea. So if we take the contribution of the new modes carefully up to this new scale for Z handle prime, and we pick mu to be able to -1, consider the rest of the paper, we have a rule for basically how the path integral is going to scale with the parameters of the problem. The ratio of the path integrals will scale parameters of the problem. So here on the term Z handle prime are with scaling, etc., but I didn't figure out factors of 2. So our relation here doesn't take this type of thing into account. This is just the scaling of the thing with the size of the wormhole and things like that. So from here, you basically just have to compute these Z handle lows and things like that for the main modes in the wormhole. It's complicated, we do it in the paper, but I won't bore you with this here. Let me tell you just that the relative contributions come from twist modes, both zero modes to the forms, like one position moduli, and some by ghosts.
Can I ask, so can you extract from this the dependence of the one determinant on the charge?
Yes, that's the idea. Yeah, we're
What is it?
well, I'm going to be telling you right now. So basically from here, yeah, the one, again, not the one determinant itself, we wrote in the paper as well, but I wrote here was the EFT coefficient, which is very closely related. But the idea is that at the end of the day, after all the settles, the EFT coefficient is just the on-shell action of the wormhole that we discussed before. Maybe some high derivative corrections that we leave there, but we didn't calculate, but they're, well, you should include them in principle. And the determinants is 3 guys that I included right here. So the first one is basically the size of the wormhole to the minus 2d. This is there for dimensional analysis. So the EFT coefficient has a dimension of minus 2d. You can basically see that from the relation to wormhole between almost operating instructions that we discussed before. So this is there because this is the scale of the wormhole, but then you have 2 loop enhancements. The first one
is the scale of the wormhole also dependent on n?
Yeah, it's like n over kappa f. I didn't write like that just because I wanted to say this dimensional analysis argument.
I see, okay.
Yeah, but it's like n kappa over f.
I
Over
see,
d
if I were to track it as a function of n, I should.
You should include this as well. Yes.
Okay.
Then we have this guy, which I really like, because the action of the wormhole is n over kappa f, right? So this guy is the action to the power of 2d plus sine of s of d over 2. Let's unpack this. So basically, 2d is the number of basically 0 modes of the wormhole in flat space having to do with moving the mounts around, right? And the rank of s of d is dt minus 1 over 2, the number of s of d generators. This is the number of twist modes. So this overall thing is the number of 0 modes that the wormhole has in flat space. So why is this nice? Because this is the action to the power of the number of 0 modes over 2. This is kind of like a classic 0 mode contribution for instantons. At least very simple instantons have contributions that look like this. So you can think of this as coming from the fact that the wormhole is some instanton with very few dimensionless parameters. Then you have one last extra contribution, which is 1 over n kappa f to the half. This is not of this form, and it comes from those 0 modes. It's a bit less unclear what the physical meaning is, but there have to be there for consistency. They also have to do with some 3 factors Poisson isolation that you get on the electromagnetic duality, and I can tell whoever is interested. But anyway, so that was the main part of the talk. So let's have any questions for this part.
Sorry, so just going back, so SOD corresponds to 0 mode associated to rotation?
Yeah. So basically, if you even have this one modes in flat space, you could have some modes which can give some relative twist between the 2 sides.
And then the D is associated with
with moving show around.
Okay.
You have D here and D here. Yeah, we got to estimate for the same thing basically by thinking of the flat space wormhole solution as well and dimensional analysis. I didn't include here, but we included in some part of the paper as well. Yeah, you can basically get this from like basic reasoning as well.
You can get the 0 mode answer, but the other part?
You can get this, and this part here. You have to calculate explicitly this whole 0 mode. It's not too hard, but you have to do it.
Sorry, and this includes the determinant of all the other angle factors that weren't.
So we basically, so whenever we have something that can be interpreted as a path integral of some local field, we use the handle rule that we discussed before. So it's not that we did hit kernel and think that get something rigorous, we just apply the handle rule. But this guy is specifically from some term that appears in the goal determinant. But this come from like 0 modes and non-0 mode contributions. Some were obtained directly, some indirectly. But anyway, if anyone wants to convince you, I also have some more arguments from the handle rule. You can basically show that it's necessary for electromagnetic duality to work, in space-time dimension. If you want to hear the argument, ask me later. So anyway, I took too much of your time. Let me tell you the conclusion and some future directions. So here we basically verify interpretation of the Cedar axion wormhole in terms of the effective operator picture, right? I think what I like the most that we did is that it is pictured that the on-shell wormhole is a sphere with two operator insertions extended around an unstable configuration. That's the prediction for the effective operator side. We gave non-trivial checks of the description by matching the phase and scale dependence of the two sides. At odd D, in even it's a bit more subtle. At odd D, because we use that new scaling argument that I discussed. We have to show that the phase of the axion wormhole has some clear interpretation in terms of the well-known stability of the axion-static universe. And we set up the problem of the wormhole determinant around the wormhole in general and discuss the role of zero and wormholes. Not so much in this talk, but this we're discussing in detail in the paper. And anyway, this will be useful for the study of this wormhole in other spacetimes, like flat space or ADS. And in D equals 4, even for the CETA work, there's still work to be done to basically figure out these wormhole determinants, including things like formal anomaly and etc., that we have not discussed explicitly. Future direction, you can ask to study wormholes in flat space and ADS as well. In particular, since flat space from this wormhole only came for some problems specific to ADS, right? The fact that the sphere has a phase and that the wormholes are and the operators are in unstable configuration, it's natural to postulate that there is no phase in flat space or ADS. I'm not sure about flat space because flat space, the effective operator descriptions, operator insertions are just basically in flat space and they have no preferred position. In ADS, it depends if they are attracted or repelled by the ADS boundary. So anyway, we project there is no phase. The phase when you are looking for vertical properties of the bilocal in the effective description, right? You just basically have a minus ITD because they attract each other. It would be nice to understand if it's some universal type of phase that exists for a bunch of other decision solutions. I'm getting another last point that I think is interesting, a bit more, out there. But well, it could be that there are these infinitely many wormhole solutions, right? With different value of n, with increasing action, negative action as increased n. It could be that by doing a statistical contour analysis that you only get a few of them in the final answer. But a crazy idea, well, maybe you could get something finite, is that you scope some over all of them. But, well, it's not clear how this would even work or how we can regularize this. But the fact that we found a -1 to the n in front of their each individual contribution is a bit bad. Because it means that maybe you could do some resummation by doing some Borel resummation or trying to think of smart way of doing another continuity sum. Oh yeah, it's 1 over n is discrete factor coming from cyclic symmetry that I told you about earlier. But anyway, that was all. Yes, sir. Yeah, thanks for your time.
Any questions for the speaker?
Maybe like could you explain the electromagnetic duality argument you were trying to give?
Oh, nice. For what? For what part?
Oh, determinant.
Yeah.
For the Handel rule? Or?
Yeah, Handel rule.
Oh, yeah.
Electromagnetic,
So basically the path integral over P forms.
sorry, 1 second. I need to move this so that everyone can see. Okay, right.
So the path integral over P forms, I'm not going to show the derivation, but you can show that it's something like that. It's basically you're going to have some non-zero mode contribution which comes from a chain of functional determinants, like this. You have -12 in the first, so the P form Hodge Laplacian, and you have the P -1 Hodge Laplacian appearing here with a factor of 2 here on the opposite side. And it kind of continues like that. But you also have some contribution from zero modes, which are harmonic forms. Here we'll just sketch the argument, what it is, and then I'll tell you more detail later, because there's a bit more. And the point is that this whole thing, and you also have a Z instrumental contribution. And the point is that this whole thing should be equal to the path integral over P tilde forms. Where P tilde is D minus B minus 2. Right, so you have a chain of determinants like that as well. So the argument, the way that we did in the paper is that you can pick T to be D minus 1 and write this relation. Then you can basically take the ratio of this between a space-time with a wormhole and a space-time without a wormhole. So the point is that most of these partial Laplacians are unchanged. Like they don't develop a zero mode, and we know this for a fact, because all the zero modes are fixed by topology. So if they develop a new zero mode, we would know. So a point is that a bunch of these things cancel, and at the end of the day, we're going to basically take have a ratio of a path integral over some partial Laplacian in the space-time with the handle and one without the handle, where the handle one has a finite number of new zero modes because you change the topology. So basically, the point is that the factors of R that we discussed are going to just match if you assume the handle rule. Another way is that you can instead impose electromagnetic duality and discover the handle rule in that case as well.
Is it like as simple as say the number of zero modes?
Yeah, the number of zero.
Like
Yeah, there we have the partial Laplacian that we're studying is delta 1 or delta D minus 1. So the point is that you don't have one forms in the sphere.
Yeah.
Because in the sphere the
yeah.
harmonic forms are just 1 and D.
Uh-huh.
But the space-time that we're studying is S1 and S D minus 1 topologically, right? So it has harmonic forms at D minus 1 and 1 as well. Oh, sorry. D0, 1, D minus 1. So basically the partial Laplacian of one form, so D minus 1 forms, has one extra mode, right? It's a zero mode. And that is like a finite, sorry. That's a new handle mode in the language that we're discussing there. But anyway, so we can basically show from this that it satisfies the handle rule. Because we know the two sides of electromagnetic duality, so we can actually just compute this. Well, we also have to assume that, yeah.
Do we know the, maybe this is again a little bit more detailed, but
The
do we
proof
know,
of electromagnetic duality?
no, do we know the profile of this like zero mode? I mean, you solve it numerically, right?
Yeah. Oh no, you don't need numerics, just.
Yeah, I mean, I agree with the handle rule, but like I just want to
Yeah,
see
the one
numerically
form-
what is the profile of the wave function or something.
That's the harmonic 1 form.
Uh-huh.
The harmonic D minus 1 form is kind of like related to the star of that.
Yeah.
Yeah.
Okay. I just want to know like if it, for example, lives almost in the
Yeah, it's basically localized to the handle, you're absolutely right.
Okay.
And we use the integral over this mode to basically compute the two sides here and then find the handle rule.
Okay.
From the duality.
I just had a technical question, which is in the slide where you show the end dependence, is it correct? I'm just not sure.
This?
Yes. Is it correct that that result is only correct for odd D?
Absolutely. For even these harder, because I'm assuming here that the path integral is univariate. It's absolutely not showing even D.
Okay, good.
So you're going to have one extra term come from the conformal anomaly in PhD.
Yes.
It will come from basically rescaling out the size of the wormhole from all the eigenvalues.
That's right.
That's an interesting calculation to do, so that's why I said here that there's work being done in D plus
The thing
4.
that confused me is that we had some, with Gabriele and Cynthia, we did like a point calculation for the one determinant, the end dependence of the little bit determinant of a flat space wormhole.
Yeah.
For these,
Mhm.
and it doesn't look like that's power. So
Yeah,
that's
yeah,
why I
yeah,
was,
yeah.
sure.
Yeah, it's a bit
of
earlier before D, yeah.
Yeah,
In this, in the first about like generalizing this to ADS, which setup were you thinking in ADS?
Still form, still charge. Yeah, you basically have some boundary conditions at infinity where you allow some flux to get there. So we still be doing things from the D minus 2 form perspective. I guess you can do from the scalar side as well, maybe that's even a bit better, but I think
It's not like the same as the usual axion wormhole, but just in ADS.
You're not looking anymore at periodic.
no, now they in the two
Those
bounds.
bases.
Yeah.
Right.
Yeah, the metric near the handle looks very similar, especially the small Q, but just the asymptotics are different.
Yeah.
But there's no, you mean with a handle in the bulk?
Yeah. So you can even think about Well, what I was saying about the phase depending if the boundary repels or attracts the operator insertion has to do the following. So we have a wormhole in AES, right? So if the handle here is very small, we can basically cut it up.
By handle you mean throat, not handle.
Yeah, yes, throat.
Okay.
So we can replace it by operator insertions and two normal AESs, right?
Yeah.
So basically, at the end of the day, if you're going to have a phase here, it's going to depend if this guy wants to be here or where it already is.
Is it clear that you can fix, in the ADS case, that you can fix the axion charge and do a fixed charge example for the axion? Since you have now an ADS boundary where you have to put some boundary condition that corresponds to using something like 9 for the axion, right?
No, but yeah, we're not thinking about the scale of the distribution. We're going to be doing everything from the D-2 form perspective still.
There's no loading condition for the D-2 form.
Oh,
Yeah, we're basically turning on to magnetic source.
yeah, okay.
Very interesting calculation.
Any more questions? Okay, not well, thanks.